Hey guys, this is my first video about the Codeforces, and today I'd like to talk about the Codeforces Global Round 12, and it is a post-contest explanation. So actually, I just solved the four problems in the contest, but after that, I read the editorials and try to understand them, and I'd like to share some of my thinking. And also, I'd like to add some comment on the editorial. You can see that I just blue coder and I just started like this semester and I have stuck in this ranking for a very long time. So I'd like to practice more and sometimes and someday I hope I can be a candidate master. Okay, so let's get started. Uh, For the problem A, we want to reorder the sequence so that there's no subsequence containing the trig-up. And we can say that the trig-up is not alphabetical sorted. So if we sort our input and it will not contain the trig-up. So the solution is quite short. We just need to sort our input and we'll get a solution. Okay, then for the problem B, it asks us to find how many operations we need to attract all the points into one center point. So one key observation is that there is only two conditions. And we can say that if in the first operation, it is we choose a center right point, and after the first operation and all those black points will be attracted into the center. But we can prove, but we can easily to say that for all other points, it is impossible. Like for this blue one, it is impossible to attract this red one because it is already out of the range of this like how about like this one? Like this blue one is already out of range of this red one, so it is impossible to attract it. So actually there is only two conditions that is possible. One is that there exists a point that can attract all of those points, and another condition is that it is impossible to attract all these points in one. And for the first condition, solution is 1. For the second condition, solution is -1. So how do we check to determine which of the condition? That is easy. We just iterate through all of the points and try to. We just iterate through all of the points as that point is the center, and calculate the distance between all of this point and all of other points, and to see whether it can attract all of the points. If it can, and we get the result, that is 1, and if not, and if all of the points cannot do that, so the result will be -1. Yeah, and that is the solution about the problem B. Okay, let's go to the problem C. Actually, this problem is pretty tricky, and even we can accidentally solve this problem, the proof is hard to think out during that contest. And one of my concerns is that I think that there may be several solutions for one test, and another concern is that like it is hard to cope with those empty position. So like if there is only 2x and actually we don't want to place an O here, but there is some empty position, so it is very annoying. And in my way, I just start with the simple case. when the grid is full of token. So for example, if it is full by full and all of them are token and there are total 16 tokens. So when we don't want the winning configuration and we want to make sure that no 3 consecutive tokens are the same. So we will just flip the first one and the fourth one. And for the second line, if we just do the same thing, and you can see that it will lead to some problem. That for the first column they are all token, and for the second column they are all X token. So that is not doable. So we want to shift them by one. Okay, let's see what it will looks like now. Okay, so if we do something like that, and it will satisfy the draw, and we will get a draw. So let's count how many flip we use. We can see that actually there are 6. So actually 6 is larger than 16 divided by 3. So it is not a satisfied flip. And how about we don't flip the first one? How about we flip the second one? And it is just a shift of the previous version. Okay, and so if we do that, we can see that it can also satisfy the draw condition, but here we just use 5 flip, and that will satisfy the upper bound. So it will give our some hint that if we try all of those conditions for the shift, what I mean is that is 0, 1, and 2 come from mode by 3, and I think there must be one of them can satisfy the smaller than the K condition. Yeah, that is my first thinking about the C1, and I try to implement it in this problem. What I'm doing is that if on the position there is an X, and I will flip that. But if on the position that it is empty, and I will do nothing on there. So, and I will try all those 3 configurations. So for first line, that is 0 and 1 and 2, and if that will satisfy the upper bound, and I will just print that as the result. And luckily it is get accepted, but I can't prove that during the contest. So when I say that in the editorial, I think the proof is very beautiful. I will use this as the example, and what it did is that it print this grid with 3 colors, the blue, red, and green, and you will count the number of X on those color will as the X0, X1, and X2, and the sum of them is K. And what we want to do is that flip one of the color as what we did here. If we flip one of the color, and we can see that it will result to a draw. Like in this example, the red one is flipped, and the proof is that we just want to take the minimum of those 3 colors and flip it. So we can say that the minimum is smaller than the average of the k. So it will give it will give the proof. Okay, then let's go to the C2. Actually, it have the very similar ideas as the C1, but here there are also all tokens on the grid initially. So what I'm doing during the contest is that I think that it must can be solved in a similar way. So I just process X and O separately. I will process X first, and I will choose the index for it, and then choose the index for the O. For example, if for the X and I choose 0 as this index, and for the O, I will try the 1 and 2, and for the X is equal to 1, and O can be equal to 0 or 2, and so it is also same for X equal to 2. And if we try all of those 6 configurations, and we can say, and I think that there must be one of them can satisfy the upper bound of the k divided by 3, and for that result we will just print that. Yeah, so that is how to solve it, but I also can't prove that during the contest, so I will also use the tutorial to explain it. Using the same idea as the C1, we print the grid with 3 colors and record the number of O and X for each color, and the sum of them is K, as here. And what we are doing is that we will separately process the X and O. So it means that for the X, if we flip one of the colors into all O tokens, and for the X, it will satisfy the draw condition. And for the O, if we flip one of the colors to all X tokens, and it will satisfy the draw. Okay. So what we want to do is that we want to select one color for the O and one color for the X, and flip them, not flip them, like to change all of those into one token. So actually, as here, we need to define another variable called A, which means that we will flip all X in the color I and all O's in the color J. So for example, here the I is green, and we count the number of X. It is 3, and the J here is the blue one, and it is 4. So the total operations we need is AJ, because we flip 2 different colors and for O and J, and let's see how to prove that it is not greater than the upper bound. We can say that the A can be represented as X and O, and the sum of A, there are total 6 different combinations, and if we represent them as the X and O, we can say that every element is counted twice, so the sum will be 2k. And finally, as what we did in the C1, we will just only take the minimum of all of the A, and the minimum element should not greater than the average of the sum. So finally, we can get the result. So let's go to the next question, D. In the contest, I stuck here for a very long time because I totally go to the wrong way. When I see this example, I think that we need to take the mean of the neighbor, and we will get the next element. And for each iteration, if we take off the mean, it will take on time, and there are total n iterations, so it is an on square solution. That time complexity will definitely exceed the constraint, because the solution should be on or on log n. Okay, so let's see the solution. So first we can see that if k is equal to 1, it means that every element is counted once, and we just want to check that if every element is from 1 to n and appear exactly once, and if k is equal to n, and it means that it will take the mean of all of the elements, so we just take the mean of all of them and to see whether it is equal to 1. Okay, so how about 1? K is larger than 1 and smaller than the n. I think that here we need some observation to decide. Okay, so let's take an example. So like 1, 3, 2, 1, and we can say that actually the 1 should only appear in the head of the tail, because and it is exactly once, because if not that, like here, and in the next iteration, the 1 will appear twice, and it is not a permutation. And how about if like 1 appear in the middle of the sequence? Okay, so in the next iteration it will be 1, 1, 2. Yeah, so if 1 appear in the middle, and in the next iteration it will also appear more than once, so it is not a permutation. And how about 1 appears in both of the head and tail, and we can see that it will also appear more than once. So our conclusion is that 1 can only appear at the head or tail. Okay. So like if 1 is here, and okay, so for this example, if we will consider the k from n to 1, so when k is equal to n, and the result is the minimum, so it is 1, and when k is n minus 1. Okay, so when k is minus 1, and when we take the first n minus 1 element, so the minimum is 1, and for the last element, that is the mean of them, that is 2. So it means that when we already check that 1 is at the head or the tail, and we want to check that the remaining element, the mean of them is just 1 plus 1 equal to 2. Yeah, so we will do it iteratively. Like if k is n minus 2, and now we are interested in 2. Okay, so we will do 2 as the same process as the 1. We will check whether it is at the head or the tail, and then check that the remaining element, the remaining is 2 plus 1. The remaining mean is 2 plus 1. Okay, and we will do it like iteratively. So when there is some at some k, and it is not satisfied, and we will just break. Because we can see that if here is not satisfied, and in the following process it will also not satisfied, like what we said. If one or if that element appear in the middle, and there will be more than once in the following iteration, as in each iteration it is smallest one, so it will appear more and more. And if it is and if that element didn't appear at all, like if there is no one, so in the following iteration there will also be no one, so we can break here. Okay, so the only remaining problem is about how to get mean in a range. And so it is actually a range minimum query problem, and it can be solved by sparse table or some other data structures like the segment tree, but it is overkill here, so the sparse table is enough. It can build the table in on log n and query by o1. Okay, and actually there is also another way that introduced in the tutorial is about use count array to record the frequency of each element, and we will go over the code later. So let's see the sparse table first. So what we are doing is that when the k is exactly 1, we will check whether each element will appear exactly once, and we will set that answer. Okay, so then we will build a sparse table, and actually I just take this code from the tourist because I think it is very clean. And what we are doing is that we want to make sure that from the orange the minimum number is 0. Actually it is 1, and I just minus it to 0 base. And after that, okay, so we will use 2 pointers, one pointing to the head and one to the tail, and we want to check whether the head or tail is equal to that num. The num is 0 at first, and if the num appears in either end, and we will check that whether in the remaining range the smallest is the num plus 1. Yeah, we just use the sparse table to check the minimum. And if it's not satisfied, we will just break. And there is the implementation of the sparse table, and for more information I think it can be found on the internet. And here I just gave one of the implementation. It is also from the tourist, but just a simplified version. Okay, so that is the way using the sparse table, and the time complexity should be the O(n) log n. And there's another one that from the editorial. So what it does is that it will record the frequency of each element. You can see we initialize it as here. And for the k is equal to the n, when we do the minimum, and we just want to check whether the 0 exists. The 0 here means the 1 in the problem, and we can set that. And for the k is equal to 1, and we also need to check whether each element exists exactly once. Okay, and so how about how about we take the mean of how about so take a mean in a range, and what we are doing is that if the current interested element is I, and we want to check whether count I plus 1 is exist. If it exists, it means that it must be the smallest element in that range. And as what we said before, we hope that I just appear at either end exactly once. So when we decrease the frequency, we want it to appear as 0. If it is 1, means that it appears twice. It is not allowed. And if it is -1, means that it does not appear in either end. It is also not expected. So we just want it to be 0. Okay, so here is the check whether it appears at each end, and here check it appears just once, and here the count I plus 1 is to check the minimum in that range. And the remaining is just the same as the sparse table. Okay, that is the solution for the D. Okay, now let's go to the problem E. I think problem E is a pretty hard question for me, and it even take me a very long time to understand the editorial. I think the editorial is very good. It proves this question rigorously and also beautifully, but it may not be intuitive for someone to start thinking this problem. So I'd like to use my way to share some thinking, and hope it can help us to think this problem more intuitively. Okay, so there are some observations that we need to know from this problem. One thing is that this graph should be a bi-party graph, because someone can have the income of an odd number or an even number, and each edge will connect to people with the different type. One is odd and another is even. So this graph should be a bi-party. Okay, let's record it. First thing is the bi-party graph. And one thing we need to notice that the definition of the bi-party graph is that all of the vertices can be divided into two sets, and each edge will connect two vertices from different sets. So it is nothing to do with the directed or undirected in this problem. Nothing to do with the directivity. So we can check the bi-party at any step. Okay, and let's model this graph first. So if it is a directed edge, and from U to V, and we can give weight to this edge, give 1. It means that the income of U plus 1 will equal to the income of V. And if we go in the inverse direction, it should be equal to the -1, meaning the income will minus 1. Okay, so how about if there are two vertices, but the edge between them is undirected? So now we cannot decide which direction to give. If the final direction we give is from left to right, and we will give the weight to here as the 1 and the inverse as the -1. But there is also another probability that this is the -1 and the inverse is 1, and it cannot be decided now, so we will just leave it undirected. Okay, and the second observation is that if there is a node, it is called U and another called V, and there are several passes between them. Like, okay, yeah. Because this graph is biparity, so it can guarantee that the different paths has the same parity of the nodes. Like they should be all be even, like 1, like 2, 4, 6, or they should be all like 1, 3, 5. Because in that way, if one of the edge is -1 and one of the edge is 1, and it will go to the 0. Yeah. So go back to our observation. So if there are multiple passes, and we want to make sure that all the distance of the passes should be the same. So it means that from the income AU to AV, from the different passes, it will all lead to the same AV. Okay. Now, and from the goal of this problem, we want to maximum this distance. Maximum distance. But as we said before, we also want to keep all of the passes same distance. Same distance. Okay, so the problem is like how to get the maximum distance. For example, if there are 2 directed edge here, and the 4 undirected edge, and how can we get the maximum distance? So maybe we can just assign the direction for the undirected edges all pointed from the U to V. And we can say that along that direction, the weight should be the 1. Okay, so now we have the left path, the distance is 3, and the right one is just 1. And we can say that we want to keep them same. So we can alter some of the edges to make them some of the longer passes to make them same. So what we need to do is to alter one of them, and it will become -1, and the 3 will also become 1. Yeah. And since in the assignment we just assign all of the edges to 1 from U to V, so we already so we want to maximize the distance. It means that before our elting edge, and the shortest path, and the shortest path here, the 1, it is already maximized along that path. It is the max distance on that path. Okay, so it means that it cannot be larger animal. So what we can do is just to decrease other passes to that shortest path. Decrease, decrease, decrease to shortest path. Okay, so now what we are doing is that to assign the weight 1 to every edge, and then cut the and then make sure all the passes have the same distance. Okay, let's record it. Want to make all passes same distance and maximize. Okay, so here comes the question, like, is it possible that it is is it possible that it is impossible to make all passes the same distance? Yes, that is possible. Like for example, if here is U and here is V, and there are 3 directed edge, and there is only one undirected edge, and we can see that no matter what we assign to this undirected edge, and it cannot reach the same distance at the other one. Okay, so how can we convert it into a formula? So let's record it here. When it is not possible to have same distance. Let's think like this one. So here is U and here is V, and we can divide the edges into 2 types in each path. One is the directed edge, and another is the undirected edge. We just sum of all of the directed edge in one path and combine them into one. Okay, so let's name it as maybe the D1, and it is undirected 1, and it is D2 and undirected 2. So we want to make D1 plus undirected 1 equal to the D2 plus undirected 2. And since for the undirected edges, we haven't decided its direction, so it is actually in a range. So U1 is greater than minus A, and smaller than A, and U2 is smaller than the B and greater than the minus B. It is totally symmetric because when all of the edges in one direction, and it is the positive, and when we inverse all of them, so it is the negative. Okay, so let's look at this formula. And let's move D1. Let's move D to the left and the U to the right. Okay, so what we want to see is that when it is not possible, so the D1 minus D2 is not equal to the U2 minus U1. One thing you can see that the U2 minus U1 is in the range of negative A minus B and smaller than the A plus B. Okay, so when we say that the d1 minus d2 is not equal to, is not in that range, so it means that d1 minus d2 is larger than a plus b, or it is smaller than the minus a minus b. Okay, so what does that mean? So how about move the d1 to the right? Okay, let's wait. How to select all of them? Not familiar with this one. Yeah, here we go. Okay. Okay, so okay. So when we use the same assignment in the editorial, which is that for the all of the undirected edges, we will assign the weight to both one in each direction. So when we look at a cycle, so what a cycle means here, we will add all of them. So that is and some of them is reversed. So that is d1 minus d2, and since in each direction the u1 and the u2 are all of the 1, so they won't change this sign. Okay, so that is a cycle. So it looks like very similar to our formula here, and we can say that in the second one, it is smaller than 0, and it is, and the previous we talked about it in the clockwise. So how about that in the counterclockwise? So if it is in the counterclockwise, and we will get u1 plus u2 and minus d1 minus d2. Okay, and we can say that it is actually same as our previous formula. So it is also smaller than 0. So it means that if there is, it is equivalent to have the negative cycle. Okay, so here, why is it not have the same? It is not possible to have same distance have a negative cycle. Yeah. And now that is all the 3 things we need to check as that talked in the editorial. Like editorial here mentions that to check the bad party and the negative cycle and the shortest path. So when we go to the code, at the very beginning we will initialize the distance, and we will set the edge weight, and then we will use the fluid washer to calculate the all source shortest path. And here we check the negative distance, check the negative cycle, And here we will calculate the maximum distance from one source. Oh yeah, I forgot to talk about it here. So since in the problem we need to calculate the maximum a minus the mean a, so we can assume that if the mean is zero, and then the max should be the distance, like max should be the distance from S to some I. So then we will try every vertices as the source and calculate the shortest path from all of them. So here may come some questions like, if we assign this as the source node, but there is some node has a directed edge pointing to it, so when it is zero, then actually that is smaller than zero, like the -1, that is the -1. So we can say that the mean is -1. Actually, it can tell us that so the S is not the mean, and that node, call it V should be the mean, but so it is not considered in this situation as S is the source. So when we consider V as the source, it will be included in that case. So we don't need to concern about that. In that case, the V should be 0. Okay. So we just need to find the shortest path from all pair. That will be enough. And the next part is about to check the bipartite. It is a little different from the editorial. I just want to check the neighbor vertices. They should have a different parity. And as I mentioned in that note, the bipartite check is nothing to do with directivity. So when we do it with the different source, the result should be the same. So it doesn't matter. Okay, so here is all the code, and I want to add a little more comment in the editorial in the last paragraph here. Like I want to explain it more, because when I see it, I feel it is a little confusing for me, because I'm not very familiar with the property of the shortest path. So here what it's talking about that is, if we already get the shortest distance for a selected source, like the source is U here, and we just assign the distance for each I as their income, and here it want to prove that it is want to prove that in this assignment it will satisfy the constraint, and the constraint is that for the directed edge, and the aj should be equal to the ai plus 1, and for the undirected edge, that the absolute of the diff of them is equal to 1. Okay, so the property of the shortest path is that the DO plus the edge should be larger than the distance, should be larger than the dv. Okay, so let's see the directed edge first. Assume there is a direct edge from U to V, and we can get two equations here. So the du plus 1 is greater than the dv, and the dv plus, as we said before, it is the negative 1. It should be larger than the du, and if we move dv and du to the same side, we can say that dv and from these two equations we can say that the dv minus du is exactly 1. And since we assign a equal to the d, so the a minus d, so it will satisfy the constraint for the directed graph, for the directed edge. Then how about for the undirected edge? The only difference is that both of the edge is equal to 1. Let's see. Yeah, the difference here, so it will look like a little different. Okay, and from these two equations, we can know that the absolute of them should be smaller than the 1, and since d is equal to a, so let's change that to a, and with the bipartity, we can know that AV should not equal to AU, because one is odd and another is even, so it will give us final answer. It should be equal to the 1. Yeah, that is the proof in the editorial. I think it is really beautiful, and it is really hard to think that during the contest. But when I see another YouTube video, I'm very surprised that someone can solve it in like 5 minutes. I don't know how can they prove that during the contest, or some other way. It is so amazing. Okay, so finally we go to the problem F. Also, I neither solved the problem E nor the problem F, but I think that the F is a little easier than the problem E, because you may can guess that property of the solution. You see that in the editorial, although the proof is quite long, very long, but the property. But I believe that many smart contestants guessed this property during the contest, so there are also more people can solve it during the contest. Okay, so let's begin. I think that there is some very misleading way you may get into if you think like this one. If you look at the last example, and you can see the answer is to take this one out and insert it somewhere else, and the problem should be 2, and the problem should, and the answer should be 2. But if you think like take out and insert, and I think that will be a disaster for you. You cannot think this problem in the right way. The right way is to think them like break and concatenate. Okay, so let's look at the first example. We can see that we break here and we just concatenate this one to the very beginning. One observation we can have is that in a sequence, if we just reverse this sequence or concatenate it with others, and there will be no gap between them because the inner order is maintained. Yeah, and when we look at the final permutation, we can see that like for the second test case, and there are 3 gaps. The one between the 1 and 5 and the 2 and 5 and the 2 and 4. And we can see the 4 and 3 is the continuous one. That is the 1 and 2 here. Because they are different tags, so we don't need to divide them. Okay, so now we want to break the original arrays into several segments and then reverse and reorder some of them. So for example, for the second one, it is 1, 1, 1, 2, 2. And so how to take the breaks? So for the continuous elements, if they have the same tag, so definitely we want to break them. So with this principle, we can just get several segments. And here we have 3 cut. The number of cut is equal to 3. And if we can concatenate them into a permutation that can satisfy that there is no consecutive tag, so and the gap, and we want to show that the final gap is equal to the cut here. I think that is easy to see because like we can let's do that. Okay, so the gap is here, here, and here, and the gap happens when we jump from one index to another not consecutive index. So they are totally same as the card. So that will be the lower bound if we can concatenate them together. And it is proved in the editorial in here. Oh yeah, actually when we cut the original array into several segments, and the only thing that we're curious about is those 2 endpoints, because we don't need to care about the things between them, and we can just use the endpoint to decide which segment can it to concatenate with. And in the editorial, the fx means the number of endpoints for each tag, And if the segment has the length is equal to 1, and it will be counted as endpoints twice, as the left one and the right one. So finally, what we have is a set of x for x as different tags. And another thing we have is k. K is a card. Okay. And in the tutorial, it just proves that in that situation when the fx is not greater than the k plus 2, and it is the necessary and sufficient but I don't want to go through it because I think it is better for you to read it by yourself. And yeah, if I explain it, I will just also read it and just show you why it is correct, but that is not necessary. And if for the other situation, like the last one, we can say that for all of those two segments, their endpoints are all 1. So it means that we cannot concat them directly. So now what we are doing is that we want to break it again. Like we break it initially into 2 segments, and we want to break it into another segment. So if we have another segment, and what we have is k will increase by 1, and the endpoints and the endpoint 3 will become 1, and the endpoint 4 will become 1. So we want to break it into a way that the neighbor element is not the x, the one here. It's not the one here. So then we can have k will increase, but for the x, it will just keeps the same. Then it will be more likely to reach this inequality. And the more we cut, and the more we can reach this inequality. And finally, if we reach this one, and then we can, and it is proved that we can concatenate them to get the answer. Yeah, so this is the final answer, but I don't want to add much comment on that because I think this editor is already perfect. Yeah, so that is my some thinking about the problem F. I think the important thing is to think like we need to break it into different segments instead of insert one element into others. That is a very misleading way.